Okay. So coming back to the slide that I showed you earlier, so Alessio's been talking about the issues around how to use getDeadline, the current interface to handle real use cases. The other thing that we've been discussing, at least at ARM for a while, is in mainline, getDeadline has a very simple view of what system it's running on. It's basically having each CPU has 100% bandwidth, and that bandwidth is the bandwidth of the CPU running at its highest frequency. Now, reality is that you can't be sure you can actually run at that frequency all the time, and the frequency might not be the same across all your cores. So there's a whole range of things that might cause you not to get the bandwidth that you try to reserve using getDeadline. I tried to list the ones that I could think of under the last bullet here. So we have DBFS, which if DBFS is not aware of getDeadline, it might run at a lower frequency than is required to satisfy the bandwidth reservations we currently have in getDeadline. I think schedutil is okay in that respect, but if you use any other governor, you're actually not guaranteed that the DBFS will make sure you have the bandwidth you need. SMT is an interesting one, because what's the capacity of an SMT thread? Who knows? So if you fill up your system with getDeadline tasks on an SMT system, you are quite likely not to get the bandwidth you thought you reserved. On ARM, we have asymmetric CPU capacities, also known as big little. So you have some CPUs that simply just can't deliver the bandwidth of what the others can. So when you want to register as getDeadline task, you can actually register something which is too big for the system to handle. I mean, you have a limited number of big CPUs that can handle 100% or 95. I think we'll leave 5% to spare. But when you run out of big CPUs, then you can still continue registering huge bandwidths, which you can't handle. On that specific topic, Luca is going to talk tomorrow, I think, about in the afternoon. On a patch set which was posted as an RFC recently on the list that tries to address that bit. And the last bit I have is about performance capping. Now, on real platforms, you're not guaranteed you can reach the highest OPP, and that goes both for Intel parts and it goes for certain ARM parts as well, that you can't be sure you can reach the highest OPP. You might under some circumstances, on others you don't know. So what do we do with getDeadline? Because at the moment we have a pretty simple interface. You reserve a bandwidth and you don't get told, well, if you succeed in registering that, then you make the assumption that it's always available. At least you don't get told if it's not. So what do we do on real systems where you can't be sure that bandwidth is there? Is that a problem for the users of getDeadline? Is it okay that you just don't get what you thought you got?
getDeadline is root only.
Yeah.
And as such, you need a system. Game coordinator. System coordinator that and you can do user space efficient control. You can basically lower, but we could easily also allow tuning the kernel efficient control to lower the maximum amount of bandwidth it gives out, such that guarantees can be made.
Yeah, so that's what I'm trying to get at here. What do we want getDeadline to be? Do we want it to be something which is fairly optimistic about how much bandwidth you have available, and every now and again your reservations just won't be honored? Or do we want to try to take it as far as we can in trying to make sure that the reservations are actually valid?
The basic mechanism, though, probably won't change. I mean, it's a matter of who is Peter was saying, who's giving actually access to
Yeah.
the underneath mechanism, right? If you know that you are on a system where you can disable SMT, no freak driver involved in anything, you can probably have harder guarantees because everything is fixed. On a mobile system, you cannot do this, but then who has the right to actually give the guarantees to users has to be aware of this thing and then maybe cope with it.
Well, I think there is one side that probably affects also the implementation, which is right now the bandwidth is allocated with a global admission control, right? So, and if we have a certain severe thermal coupling, it can be that whatever bandwidth is available on single cores, even if you sum it up, is not really enough to satisfy the requirement of one single task.
Yeah.
So it's still admitted but not fit the guarantee.
For that, do you know if there is a always guaranteed set of OPPs that should in principle always work? Because then you can probably work with that.
So that's a hard question, but well, there are some sustained performance levels. I think in ACPI, I think there is the possibility of exposing a sustained or guaranteed performance level. On the ARM side, in the SCMI spec, we have an option to specify a sustained performance level as well. How you determine what that level is a separate discussion, I think.
When you have severe thermal trapping, often you will reach the lowest OPP.
Yeah.
So that's going to be your two-state.
Yeah, that's what I'm saying. You probably don't want to go into those situations.
Exactly, because if you look at pixel phone, for example, the lowest OPP on the big CPUs is like 10% capacity, right?
Yeah.
And that means you can't admit anything bigger than that.
What I'm saying is
And
that
makes
maybe
the
we
class just
So we don't do that on the little though, so you kind of can sustain the biggest.
because what I'm saying is that if you don't have any notion of how the task can actually be, then maybe you can go faster for some time than you throttle with deadline. In principle, at least in theory, you should be able to say, okay, I don't ever want to go this fast just because I know that I don't need to go this fast, and then maybe I'm ever throttled, so I don't enter that.
Can you please speak louder?
Yeah, sure.
There's another problem trying to make the admission control kernel to be sufficient but not necessary, because when you do this, you be pessimist. You may be over pessimist, and you might reject one task that is not that would be scalable. And the point is that as we support global in single CPU or clusters, we might have different admission controls that might give different results. And one might have, if you want to implement this all in kernel, one might have to have one knob that selects, okay, I want to use this admission or that admission. And that doesn't scale well, I think. That's why doing in user space, it would be easier.
Yeah, what I'm not sure about is that even, let's say if you are pessimistic, but you have, you say, okay, I can reserve 95% of my system. But that's not the case for example, mobile, because you cannot really run all the time at 95% because that's not, I mean,
So
we can't do that
what level of guarantees do you want your system to have?
Yeah.
But it's not really by system either, it's by workflow. So Alessio actually presented last year a use case for Android, which is audio. And I think for audio, we would really want something more like the harder guarantee for the low latency audio, because the musician doesn't want to hear his stuff screwed up at all.
Right,
And we can't miss
but can the system provide this? I mean, if you're charging the battery, place it in the sunshine.
In Brazil.
At some point, in Brazil, at some point the system's gonna say, well, screw you guys, pound sand. And the musician, so
I think in that case, if it just can't do it, I think we serve the musician better by saying, we can't give you
probably
your good audio under these circumstances. Maybe bring a refrigerator on stage with you or something.
So, but yeah, it's up to the device integrator, and I mean, if your phones are so underpowered.
That's true. And so for the audio one, I'd say it'd be better to say no, I can't do it, rather than to try and just have it sound all glitchy. For the video pipeline that we talked about today, I think it's more acceptable to say, okay, we can't do it, we'll just keep going as best we can. And so, even on one system, one kernel, we have different policies we want to enforce. course based on workload.
I guess maybe also what Daniel was saying is that depending on your use case, you can be more relaxed on how many things are passing the admission control. Like in the audio case, you just want that thing just to work. So if you gonna realize that it's actually asking for too much, you say just no, and maybe change your condition or
the criticality, and we don't support that yet.
Yeah, but if
yeah, I'm not saying that everything is right, just use it. I'm not saying that, but still we have to understand what we want to do.
On Android, who gives the priority? Each task can ask for its priority, or there is one?
So no user code can ask for anything. We don't because we know that if we provided that, they would all say I'm the most important.
There is
so we don't provide that. So it's a system level thing, and RT, anything that runs RT or deadline is very carefully determined by the framework.
Oh, and this you could implement these admission control tests in the framework and select on the framework, and then the framework would allow or disallow someone to run.
So for these use cases, yes, it would be very it can definitely be managed by the framework.
But if you do something in framework, then we still have like native API, so you're not really sure that there can be some other threads that it's generated maybe by platforms, integrators, and whatever that screw up your user space view of the vendor. Okay, I mean something in kernel space would definitely be more safe in general.
No, I'm just trying to. I'm not against. I'm just trying to show the other side. When you try to have a lot of admission control internal, because they are not optimal, you might have like a fighting on admission controls and a lot of knobs to select admission controls, and this does it still as well.
I think it's more, maybe it's too harsh to say guarantees, like we can for sure guarantee
No,
that.
just showing
the scenarios like Brazil under the sun is probably very unrealistic, but there are scenarios like if you use a VR headset right now here in this room, which is good or whatever, we already cap quite a lot on Android to sustain the performance for, let's say, the next 20 minutes or half an hour, right? It's not really happening right now, but we know that we are going to do this activity for the next half an hour, and so we need to cap the frequency. And those capacities will not be available to deadline either. If we have deadline tasks for those, these are like middle ground settings and capping that we should probably consider and find a better way to define them.
So sorry, just I think that one issue is that there are two kinds of admission control. One is for not overloading the system. So you don't really provide guarantees to real-time tasks. You just ensure that your no real-time tasks are not starved. So something can be done. There is something that can kill some tasks or do something to recover the system. The other kind of admission control is to provide guarantees. Now, providing guarantees is difficult, but so maybe you can have some user space stuff doing more advanced admission control, but not overloading the system, so not starving everything else. I think it's important in kernel space. And I think the current admission control is missing something there. I'll talk a little bit about this today in my talk. One simple thing is that it doesn't account for the CPU capacities on asymmetric systems. So that's the easy part. The thermal throttling is another issue that can compromise the system by overloading it. So I think something should be done there, and I'll propose something this afternoon. Anyway, just to say that I think we need to split not just weak guarantees and hard guarantees, but no overload versus guarantees. That's in my opinion.
There's also IRQ account that is not in account.
Yeah.
There are other workloads that end up being like in a higher priority than DL, like IRQs and stock machine that are not accounted in the admission control for the avoiding problems. Yeah. I agree.
Okay, so we don't want to stop the discussion.
Okay. So I think, well, one important point I think is that capping is not something that happens in extreme cases. It's going to be normal, just like Patrick said for VR use cases with handsets. We are capped all the time. So just assuming that it's not going to happen, that's not a valid assumption.
That's something that your device knows. We don't know. The kernel doesn't
how would they know that? Some of the,
What kind of shit system they're running on.
they might not.
If they're charging the battery, or if we run for 10 minutes, there's no CPU power left.
Mm-hmm.
So the system integrator, Android in this case, they can do something about it. They can say, if we want guarantees, we can only use very bare minimum OTP.
Yeah.
Doing the global bandwidth.
No, just I mean, the user space access control.
So you want some gatekeeper in user space that does this instead of putting it in the kernel.
Well, yeah.
Well, that's an option. We just have to pass a lot of information into user space then.
One of the kernels should just ensure that the system doesn't blow up, basically.
What's blowing up? Is that just missing your reservations, or is?
So we already don't do that anyway.
Maybe what Luca was saying, at least not starting completely the system. You have something is always reserved for potentially unblocking bad situation
Yeah.
with the other type of guarantee.
But yeah, I mean, the extreme throttling stuff, that is just really unfortunate.
Yeah, I'm just worried that if we just give in and say we can't guarantee anything and we go down the completely weak guarantee route, if get deadline ends up being unusable for certain workloads. Whereas there are ways, if we try to make the admission control more aware of what the hardware can actually provide, then it might become more useful for those workloads, and there are various ways to try to give you something which is slightly more flexible. I mean, there has been talk about demotion, right, where if you use up your reserved bandwidth, then you can continue running as a CFS task or something like that. So is it so bad that you can't reserve 80% of a CPU?
Not at all. But I mean, if your actual guarantees are like 5% because of the extreme throttling cases, then it might also not be useful in the normal circumstance.
Yeah, yeah.
But even just the case where you have a task which is submitted, let's say it's a 60% bandwidth requirement, but because of throttle whatever, we don't have in any CPU 60% capacity available. It's only 55, right? So you blow up even just a partitioned CPU or whatever it's called, like a per CPU CBS. That's already a big improvement.
But I think that's what I was saying. I mean, if there is a way to know that 60% is the sustainable thing, then I guess it makes sense to try to use that information to admit less tasks, because then you admit only what you can actually guarantee. If you have the information, I mean, for example, for capacity, you have the information.
Yeah.
What Luca is doing is try to...
But it's going to be dynamic, right? So because when this thermal throttling starts, you already admit it. So in that case, the application has to do
if
that.
there is a sustained thing that you know that you can maintain, then you can do this. If there is not
If
this
you can't admit
thing,
a useful enough because it's too low, then what's the point?
You can have systems where you have 4 CPUs little that provides a 20% capacity, and a very big, huge, massive CPUs that provide the 100% capacity. And when you are on those thermal throttle things, you switch off the big CPUs, but you still have like 4 20% CPU, which is 80%. So you cannot meet a task which is 40%, it will never meet the guarantees.
Right,
and if you say the maximum bandwidth is 20, it's too conservative.
yeah, but then what you want the admission control to do? I mean, admission control is, at least to me, something that if you pass it, you know that there are some kind of guarantees. Might be not the hard real-time one, might be soft real-time, because it's not, I mean, there are a lot of things going on, but at least some sort of guarantees. If you're saying that, okay, I missed something, but I know that I cannot really provide this type of guarantees, that's
You
really...
can just say you will meet your deadline in a normal scenario that is non-thermal cap. Right? And as soon as you get into thermal capping, then you get into some,
The problem
degraded mode or something.
The problem of pretending having all these things in account into many different admission controls is that it will get very hard to have this admission control running over the time, and mainly because it will depend on this application or that application.
Why does it depend on
Because
the
one
application?
processor can have this sustainable, other processor does have this property of thermal, and this workload has this property of this thing. So if we try to always assemble all these properties into a very complicated admission control, it will not be sustainable over the time to maintain its admission control. We are starting having conflicts between one metric and another, and having these all inside the kernel, it's even a higher complexity. So having these in user space, it will be more flexible for users or for each application to change the admission control on the way that they want.
And
so
then
you
from
will
user
add-
space, you need to be able, for example, to pin a task to a certain CPU.
Yeah, if
It's
you
like-
can just
But
disable
that-
the
that you can do
admission
it.
control and do
If
the
you
control by
disable
yourself.
the kernel admission control, you can do whatever you want. I mean,
Yeah.
you are to know what you're doing, but then you can do
You
it.
are your own king.
So, and the kernel one can be simple and just to avoid new starvation.
Trouble, yeah. And then you
Oh.
can do whatever you want.
But if I play a game on my phone, am I always running on the little cores?
No.
Is it slow?
Depends on the game, I guess.
So with gaming, one of the challenges and one of the things we're working with them is giving them feedback on the thermal state so that they can, because the gaming guys can draw less stuff to reduce the pressure on the CPUs and on the system. And so if we have a good feedback loop with them, which is something we're working on, we haven't got there yet. So as you're sitting in your hot car with the windows closed and the sun shining and the thermal pressure is building, the game is getting feedback, and what you're seeing is maybe a little less resolution. The explosions are a little blobbier instead of all the detail of the flames. But you're not janking. You're still able to play your game. So I don't think we're using deadline for those games anytime soon. In fact, I don't see us using it for just sort of general purpose application stuff. It's these very specific pipelines that.
No, but yeah, no, I was just thinking, so because if the thermal stuff is so deadly, as it was thought to be, then gaming would be almost impossible. I mean, if you
Yeah.
charge your phone and have the screen on bright and play a game, the CPU would be almost dead.
Yeah, so the way, the good news is we don't have to just sort of impose these low frequencies on them. We're sort of negotiating with the game about just using less resources as we're rotating it down so it's not, this terrible janky experience. And there's other workloads we can do that sort of thing with. And I think for deadline, for like I said, for the audio case, I think there's a admission control. It would be specific to audio, and we'd say, sorry, can't do that right now. Tell your bandmates to turn on the AC.
Or use a real computer.
Or use a real computer.
Maybe should we add, so to implement this mechanism for hard guarantees, we can return a group keys, also provides more entries, which I really likes to be, that tell you what the hardware guarantees for you.
That's what you already have in SCMI, and you have it in ACCI as well. So the information is already there, it's just not being used. And if you want to push this whole thing into user space, then we need to expose all this stuff to user space somehow.
I'm afraid that the only way to have really high guarantees would be to have a very complicated, very complex algorithm within the hardware by itself. I mean,
We can never provide real hard guarantees. What I'm thinking is, how far do we want to take it? Can we provide guarantees so far that the problems you are facing, if you get that far, are actually not whether your reservations are valid or not? You have bigger problems. I mean, if your phone is so hot that it can't do anything and it's going to reset or turn off to protect itself, then we don't care about the guarantees anymore.
What I think is that, so as Daniel was saying, there are many different kinds of admission controls. Also that if you start...
It's complicated.
It's complicated.
Admission control, it's complicated.
Yeah, but it's going to be complicated in user space too.
Yeah, but it will gonna be complicated. User space or in kernel space. But in user space, you can do whatever you want.
Except that you don't have the information you need.
No, so the problem is not having it in kernel, it's having information.
Well, that is true. Yeah.
But some of the information you can read from the kernel today.
Yeah, so if you have the information, you'll be able to do user space, and you not
Well, you
need
need to
a
expose it to
user
user
approval
space,
to
yeah.
have your algorithm running.
So
But you need to expose that to user space as another API,
Yeah, but-
where today you can
yeah.
just read it from the tables from wherever they come from.
Yeah, I
Well,
think that the
We
problem of
started
freedom
out
is
with
is
the tables
smaller.
not even knowing.
Well, it can be in the tables.
It seems to me that the problem sort of involves user space and the kernel at the same time. And we need to split it somehow. The solution is there too. I mean, part of it is the kernel and part of it is user space.
yeah, and involves also the application.
So the major problem is how to divide the problem between user space and the kernel.
Yes.
Okay, so in these words, I'd say that it's easier to provide information to user space than writing admission control and having the approval of this admission control for a very generic scheduler. Let the scheduler be just the simple things, and let do the things in user space.
But we are talking about you need to implement a scheduler in user space too, because you need to do pinning and all sorts of stuff in user space.
But let's put, as you said, if you have the admission control and you do it by yourself, you can overcome the limitations of affinity. The problem of affinity is that it's very hard to have a global arbitrary affinity admission control. We don't have this in theory, and there are like
Paper by Bjorn? Bjorn? Confess. Confess.
Anyone from Anderson.
There are a lot of constraints that are not real.
But also task dependencies. You know, when a task suspends waiting for the GPU. So if you want to consider all that stuff, it's going to be very complicated. I mean, admission control is overly complicated.
Yeah.
If you want to make it really hard side, like on the hard guarantee side, and it will likely push you towards getting reservations that are very over-provisioned, you know, pushing the actual utilization of your system much lower than it might, you know.
And also, I mean, even if you make the kernel admission control very complicated and actually it takes it all into account, then after, let's say that you meet a task, and then right after that thing, your family throttle. So when what you omit is already out of the window. So why making this thing complicated if you cannot then guarantee anything?
But
So,
if you have these things in user space, you can just avoid the thing that we have in kernel now and say, okay, I know that my task will schedule if I pin this on this way, and even leaving something with global and something pinned. If you guarantee this in user space, you can just turn off the admission control on the kernel and be happy.
No, I mean, you'll have the same problem basically, just moving the problem to user space. But then,
But then you will
the
not
kernel
have
side
problems
is
with
simpler.
the sustainability of the scheduler in kernel.
I have another general question. When we have this thermal throttling, is it like we only cap CPU frequency down and the capacity of the CPU at that frequency is still untouched, or does it happen that you cap the frequency down and the CPU goes actually slower because of, you know, under thermal throttling? So is it only like we lower the CPU frequency, or is it also the case that the capacity we knew about in the kernel is not valid anymore because maybe the CPU, I don't know, goes under protection, disables something further or whatever? I don't know, just asking.
Like, I mean, so in most Android systems, you're either just capping the frequency, or some of them are hot plugging out CPUs. Those two are the remedies. Now, what happens inside the core on thermal? If there's some hardware or firmware stuff that's happening, I don't know. But the remedies that Android uses are capping on the big CPUs, typically these days not on the littles, and hot plugging big CPUs.
So when you cap the capacity of a little, actually Luca has a very nice example where because of capping you have capacity inversion. So big CPUs are smaller than little CPUs, and these were convenient to run the task on little CPUs than big one if you want to really be faster.
Interesting.
Yeah, it's complicated.
This gives up everything.
So
We are
we're probably running out of time. Yeah, I'm not sure if we should have put hard guarantees up there. I think the question was really how far do we want to go in kernel, because as it is today, you can very easily make reservations that that can't be honored. So how far do we want to go kernel side to try to help the user? Because as it is today, you need to know about all the things I listed on the other slide to actually know whether your reservation is going to be guaranteed or not. So we could as well just not have admission control.
Lucas patches go a long way to fixing it.
They fix Big Little without capacity capping, without SMT.
Does Big Little have SMT?
No.
Okay, so,
But you have the problem on your Intel cards.
I know. So for most of the real-time people, they globally disable SMT.
Yeah.
If we do core scaling, we can trivially fix this. Other than that,
But you also have turbo states, so you have that problem too.
yeah. So
And then some of your parts
It's,
are.
it's a little different in that there we're typically always running the highest P state, and just turbo states is giving us above and beyond.
Yeah,
Whereas here
but the top OPP, if you look at the laptop parts, it's like
I'm just saying
40% of your peak
it's
performance.
slightly different
Yeah, the
Turbo state is not
but
accounting the
40%
global
is still a
activity.
significant
because
amount.
it's just transparent to us.
Yeah, it depends on what you're doing.
But if you want guarantees,
state governance.
that's what you get.
Yes, but then why not put those 40% in the admission control to make sure that you don't make reservations that exceed the guaranteed performance?
That might mean that on the Androids you get such a small thing that it's where do you want to place the guard? And I think that's for device.
Yeah, it will be. But not telling the user anything, is that helping?
So far the user can't use deadline anyway.
No, but if you want to use get deadline or
Eventually, yes.
yeah. Anyway, I think we're out of time. There'll be more.
Slide,
Sorry?
was there a fourth slide?
There was a couple of other slides actually, but not very important.
Well, maybe can I just call out one thing on
Yeah.
RT, then maybe we can have a discussion. There is another
Yeah.
slide after. So we have a couple of discussion points regarding RT, how we can try to improve it. One of the things that is completely missing in RT is also like capacity awareness in general. So the question here is, can we think about and try to experiment some mechanism where when a real-time task wakes up, instead of going to a random idle CPU, maybe we can, not idle, sorry, we prefer active CPUs over idle, but let's try to maybe prefer a big CPU if it's available instead of a little one. And this means, well, investigating what can be the mechanism. In our view, one mechanism can be like using util tran for bias task placement.
Here in the previous discussion, I would say you need to prefer a little CPU because for guarantees they
right.
are.
But for RT tasks, sometimes we have in Android RT tasks that are very short, small tasks that are just trigger some external accelerator, whatever. And if we run them on little, we also have other things like CFS tasks convert to little because they follow RT tasks, and that's not really usable. So we can bias somehow without strictly pinning them RT tasks and do capacity awareness placement that can be interesting.
I mean, we can do all sorts of. I don't know for RT because RT is such a piece of shit.
It's good.
It's a horrific scheduling policy. It does everything you don't want it to. From an operator, it's a horrific thing. I don't know.
Well, you are not completely again, so if you can experiment a little bit and try to find something that you can I'm not saying Thomas is not here, it would be against probably. Okay, we'll try something eventually.
I know one thing we've been doing in Android is on RT is at least avoiding ones that currently are running soft ins or something else that just induces latency instead of I think we've done a few capacity oriented things there as well. But
In previous pixels, yes, is not there, but we would like to explore.
that soft in one's been kind of important. So
Yeah.
maybe we should push that aside.
Yeah, clamping is one option potentially, and if you can make it like tracker, you can disable it, the clamp can be actually disabled. You can maybe try to bias task based on using the clamp and task here and there.